Now, let's move on to the next period in the history of Mars, the Hesperian. This period began 3.7 billion years ago and ended 3.2 billion years ago. As the late heavy bombardment waned, volcanism replaced impact cratering as the main surface forming process. Volcanic activity released large quantities of sulfur dioxide and hydrogen sulfide, resulting in sulfur-based minerals replacing the earlier phyllosilicates. Most of the water bodies present during the Noachian had dried up, and had the Arabian Ocean existed in the northern lowlands, it was gone by the start of the Hesperian. However, in the early Hesperian, major volcanoes such as Olympus Mons formed on the Tharsis Bulge and underwent a long eruption. This eruption released water vapor into the atmosphere, which rained down on the eastern side of the Tharsis Bulge and formed massive outflow channels as it flowed into the northern lowlands. We can still see these outflow channels in places such as Cassi Vallis and Vallis Marineris. Eventually, enough water had flowed north that the Deuteronilus Ocean had come into being. You may have heard that this ocean was too salty to support life, but while it was saltier than the modern oceans, it was less salty than the Dead Sea, since we know that contrary to the name, the Dead Sea harbors life. Although it may have been too salty for life to begin in, once life had begun, it could adapt to survive in the Deuteronilus Ocean. Over the course of the Hesperian, the magnetosphere weakened, allowing the solar wind to strike the atmosphere. The impact of this was twofold. The atmosphere became thinner as more gas molecules blew off into space, and given that the lighter, more reduced gases were more likely to fly off, the atmosphere became progressively more oxidized. So, what could a hypothetical Hesperian biosphere look like? Around this time on Earth, we find fossilized microbial mats in coastal sediments, indicating that life had begun to emerge from its hydrothermal cradle. Furthermore, molecular analysis has indicated that life on Earth reached a level of complexity on par with some modern organisms. This means that if life existed on Mars, it could have begun to colonize the Deuteronilus Ocean. Any organisms which inhabited the ocean would have been halophilic. Near the surface, phototrophs could have used light to power their metabolism and produce biomolecules from methane and carbon dioxide. Further down, fermenting organisms could break down biomolecules back down to carbon dioxide and methane as an energy source. By the mid-Hesperian, any kind of organic haze would have been removed by the progressively oxidizing atmosphere, inundating the surface waters with UV light. This would decrease phototrophic activity, but it would also produce a redox gradient between the atmosphere and mantle, which Martian life could harvest. Sulfuric acid raining down into the ocean could be used as an electron acceptor to oxidize either methane and hydrogen being emitted from volcanic vents or organic matter. In the late Hesperian, parts of the surface would have begun to become oxidizing, and dust blown into the ocean could deliver iron oxides and perchlorates, which could then be used as electron acceptors for the oxidation of the aforementioned chemicals, as well as hydrogen sulfide or ferrous iron. There is some debate among planetary scientists as to whether the Hesperian-Amazonian boundary should be set at 3.2 or 2 billion years ago. This is because by 3.2 billion years ago, the Deuteronilus Ocean, along with all the large standing bodies of water, had dried up, volcanic activity slowed, and the atmosphere had thinned, allowing large amounts of radiation to hit the surface. However, for the next 1.2 billion years, there is evidence of continued hydrologic activity driven mostly by condensation into ice, forming glaciers, and subsequent melting followed by evaporation. So, during this time, liquid water would have still existed on the surface as ephemeral meltwater rivers and hydrothermal pools. This water would have been acidic and salty, but at least some of it would have been habitable. This gray area between the wet world of ancient Mars and the hyper-arid Mars of today has led to disagreement as to when the quote-unquote modern period of Martian history began. But how could life have survived during this time period? With organic carbon no longer abundant, intuition would suggest phototrophs might start taking electrons from other elements such as sulfur, iron, or even oxygen in the form of water to produce organic carbon from carbon dioxide, giving rise to photosynthesis as we understand it. However, being exposed to sunlight would also expose any organism to intense radiation, making any photosynthesis highly limited. When we look at microorganisms in some of the most desolate environments of today, we find that many oxidized trace gases in the atmosphere, such as hydrogen, methane, and carbon monoxide. Now, if Martian life was to use the same strategy, it would require oxygen. It's commonly stated that the water on Mars was blown off into space by the solar wind, but this is a misnomer. High in the atmosphere, water molecules would have been split by energetic particles, and the lighter hydrogen atoms would fly off into space, leaving the oxygen atoms to recombine as molecular oxygen. Now, this oxygen wouldn't accumulate to become a major constituent of the Martian atmosphere because it would react with iron minerals in the crust to form the hematite that gives Mars its red color. But even if it was only 1 to 2% of the atmosphere at a given time, it would have still been enough to oxidize the trace gases. Many environments on the modern Earth have similar conditions to that of the early Amazonian of Mars, and can thus provide insight into how microorganisms could have survived. Across the world, fresh glacial tills and runoff streams can elucidate how Martian organisms colonized similar systems over 2 billion years ago. One particular environment that is of interest is the Rio Tinto River in Spain due to its acidic conditions and high levels of iron oxides. Another analog would be Yuyaco, the highest volcano in the world. Near the summit, there are vents known as fumaroles, which emit volcanic gas and water vapor, which sustains the highest phototrophic communities in the world. Similar communities may have existed on the dying Martian volcanoes. The Uyuni salt flats in Bolivia host hypersaline groundwater, and microorganisms here would face similar conditions to those inhabiting the dried remnants of the Deuteronilus Ocean. Finally, in the Mepinong Cave in South Africa, microorganisms oxidize hydrogen gas using sulfate from various minerals as an electron acceptor. 2 billion years ago, similar environments on Mars could have acted as a sort of way station for the colonization of the deep crust by Martian microbes, and later in this video series, we'll discuss why that's very relevant today. But what about Mars today? Could we find living organisms on the planet? One reason many believe that the surface is sterile is the scarcity or possible absence of liquid water. The triple point of water is 612 pascals, and below this point, water cannot exist as a liquid. This means that liquid water can only exist in the low altitude regions like the northern lowlands and the Hellas Phoenicia, and even there, it will only be liquid for a few degrees above zero before boiling. No precipitation has been observed on Mars. However, frost has been observed, and should this melt, it will provide a temporary source of liquid water. Gully-like features have been observed on Mars, but whether or not these were formed by liquid water is an open question. Experiments have shown that microorganisms can reproduce at pressure slightly above the triple point of water, but not below. Although liquid water will be scarce if present at all on the Martian surface, one strategy Martian microorganisms could employ is to produce their own. Given that microorganisms in arid environments on Earth oxidize atmospheric hydrogen for energy, it's been hypothesized that they use the resulting water produced to meet their hydration needs. The concentration of hydrogen in Earth's atmosphere is 0.5 parts per million, while on Mars it is 15 parts per million. However, since Earth's atmosphere is so much more dense than that of Mars, the partial pressure of hydrogen is 51 millipascals, while on Mars it is at most 17 millipascals. Should Martian microbes be able to use hydrogen at these concentrations to fuel methanogenesis, for every gram of dry weight they'd produce, they'd also produce 5.4 grams of water. And given that bacteria are roughly 80% water by weight, this could theoretically meet their hydration requirements. But even if Martian microorganisms can survive in such a dry environment, there are other obstacles to survival as well. On Mars, there are many salts that include perchlorate ions, which comprise 0.5 to 1% of the weight of Martian soil. To put that in perspective, the soils in the Atacama Desert are on average 0.02% perchlorates by weight, with the nitrate ores having the highest concentration at 0.6%. There is an ongoing debate as to how Martian perchlorates were produced, but the general consensus is that the reactions are photochemical, involving UV light, chloride ions, water, and possibly carbon dioxide. Perchlorates are powerful oxidants, making them very toxic to living organisms, but they can also act as an antifreeze, expanding the range of temperatures at which liquid water can exist. Furthermore, perchlorates can be used as electron acceptors in microbial respiratory processes. However, experiments where microbes were grown in perchlorates used concentrations less than 10 millimoles, while the concentration in any Martian mud would be greater than 50 millimoles. But even if microorganisms were grown in solution with Martian perchlorate concentrations, it still wouldn't rule out the possibility that perchlorates prevent Mars from being habitable, because, as we're finding out, the limits of habitability may not lie on a single axis. Most of us are familiar with the saying, life finds a way, but emerging and controversial research is indicating that there are environments with liquid water present that don't harbor any life. Some of these environments are the Dalal pools of Ethiopia, where no microorganisms could be found living in the water column. The most likely explanation for this is that the pools are both highly acidic, with a pH of around 0, and hypersaline, with a salt molarity of around 15. While acidophilic microorganisms can survive in environments with the same pH as the Dalal pools, and halophiles can survive in water as salty, no organism has yet been found that can tolerate both the acidity and salinity. So, when identifying the limits of habitability, we likely have to look at a combination of factors. Another environment that has been found to be sterile are parts of the McMurdo Dry Valleys of Antarctica. Like the Martian soils, the soils in the dry valleys are hyper-arid and have high levels of perchlorates. While organisms may be able to survive in environments with similar levels of perchlorates, repairing the cellular damage which they cause requires a lot of energy that just isn't available in such a desolate environment. On Mars, a similar set of hardships may very well render the surface sterile.